Sorry about that. Sorry about the first couple of pages, maybe 10 pages, but it's just analysis, so it should be fine. And then let's see the Philippines. The Philippines has a similar situation. However, it's not like hugely serious compared to Japan and South Korea. So be more manageable. So this is why we need to have a proper mix of renewables rather than just one single source. If we have only solar power, then it can actually create trouble like Korea or Japan. But if we have more wind power around the country, because the correlation of wind correlation is much lower than solar correlation, even in a small area, so that it can create a bit create less problem. I wouldn't say it will not make problem, but it will make problem, but be more manageable. And in terms of Pakistan, what I found interesting is, I mean, wind is becoming a pretty important energy source for Pakistan as we have a higher wind share. And then actually wind becomes like peak demand. Actually, this is not peak. Peak is always gas. However, wind becomes more like intermediate power source, which is very interesting to see. So yeah. And then next one we need to see is a capacity factor. In case of Indonesia, there is no real change as a renewable energy capacity itself is not, renewable energy capacity doesn't change much. In case of Japan, there is a huge capacity change or capacity factor change of bio and coal and also hydro and nuclear as well. In terms of nuclear power, going down to 65% of capacity factor is not really technically feasible because usually it needs to go more than 80% almost always because economically it's cheaper. However, somehow it can be controlled like France or Sweden. So Japan might need to introduce more like a seasonal nuclear power management operation or plan or something like that. But interesting point is core basically becomes almost useless in Japan. And probably same for South Korea. What I found interesting is this gas is becoming I think this need to be this probably was wrong calculation. Gas is becoming much less important in terms of capacity factor. However, lower the capacity factor of gas means higher the S&P due to more expensive power output of gas. Does it make sense? So when you install gas, basically overnight cost is fixed, right? The reason that I'm talking about gas is because gas is almost always is a S&P decider. So gas price becomes the S&P almost always because gas is the peak. Gas provide a peak generation. So overnight cost of gas is fixed, right? But if we use like if this gas generator provide 100 megawatt hours of electricity every year, then probably you might need to the cost can be something like $100 per megawatt hour. It's just a random number, okay? However, if gas generator provide only half of it every year, like 50 megawatt hours per year, its fuel cost will go down. However, this gas generator still needed to pay the overnight cost, right? So that it becomes so that gas price becomes more like $75 per megawatt hour rather than half, like $50 per megawatt hour. So if gas power has a lower capacity factor, usually it means S&P is going to be higher than before. That's something very unfortunate. And in case of the Philippines, I found something interesting so that I have this output. So the output that I wanted to share is the output from somebody. 9%. Thank you, Manju. And do you, as per economic survey, Pakistan can generate 50 gigawatt Wow, that's huge amount from gas, from wind. So let's assume it's 50 gigawatt. If we go back to Pakistan, basically almost everything can be turned to wind, as Pakistan has a quite good amount of hydro, which is um, 11 gigawatt. So if it is well managed, probably hydro and wind can be a major source of electricity of Pakistan, I think. That's a good news. It'll be very interesting to analyze the power power network of Pakistan, how this can be dealt with. Thank you so much. And this was the output. I'm not gonna see this. Not this one. This was the output from somebody from the Philippines. The reason that I want to share is because this is the output capacity factor. And then you can see the capacity factor becomes higher than 100%, right? Capacity factor never can go more than 100%. And technically, usually, except nuclear power, 80% is pretty much the maximum. In case of nuclear power, it can go up to 99.5%, which what happened in South Korea when there were not enough power generators about 20 years ago. Other than that, usually 80% is normal. So this is one way you can validate. You need to use your own knowledge. And if you see here, wind becomes 117% and solar becomes 87%. But usually solar power generator doesn't go up above like 15% in South Korea. And in case of those places where you have really good sunshine, probably solar power can achieve up to 28 to 30%, but no more than that. So in case of wind, if wind quality is really great, then probably 45% to up to 50% is the maximum. However, 117 is not is not really reasonable number. So that I checked what happened, and thank you for sharing your code. This is very valuable. The first code was perfect, right? Network BAU generator divided by network BAU generator, the power, so capacity. However, the second line, there was an error, or we call this is not error, this is a bug because it worked, but in a wrong way, right? So network, so this training divided the generator of network renewable with network BAU. So used wrong capacity, right? That's the reason why we have some wrong number here. Thank you so much for sharing this. And this is really valuable to everyone. So just have a look at it. Thank you, Manjur. We definitely need to have a chat later about the Pakistani's power system. Could be very interesting. So this is something that we can find almost always. So as a modeler, I'm telling you because this is the last session. As a modeler, when you run it, just see the result and don't believe it. Just assume every single number is wrong. Just assume it. And then double check it if those number is actually wrong or correct. Right? Otherwise, you are going to write a report or you are going to bring this output to a Minister of Energy or Minister of Climate Change or Environment with wrong numbers, right? So you need to make it sure that your every result is technically correct and very sensible and yeah, based on your knowledge and based on any calculation. The best way for me is always I assume my calculation is always wrong. And then do it again in a different way. Or sometimes I calculate on a paper because it doesn't mean that I don't trust my computer, but because I don't trust my fingers because it always make mistake, as you could see during our 8 weeks, right? So, and then, yeah, Pakistan, we have Pakistan. As you can see, solar capacity factor is 17% and wind is 23%, which is a pretty good number. But these numbers are not really correct number because I provide sample wind and solar potential. And as you can see, bioenergy capacity factor dropped hugely and coal dropped a lot. So what we can expect actually is huge drop of a huge reduction. I mean, huge. I wouldn't say huge. I use that word too much. Um, we can expect the CO2 emissions drop. Okay, that's what we can actually see, and we are going to calculate it from now for the next 20 minutes, and then we'll jump on to the last part. Okay, let's calculate the total emission. It's page 21. Come down to page 21. You guys are still on page 19 and somewhere above there, so page 21. So we are going to calculate the emission and each emission intensity, but yeah, emission and total emission intensity. Let's do it one by one together. We are going to use the previous code. So if you have your own code, please run on it, and then let's go through it one by one again. Going to run until the last line so that I can have all the output from the previous week. So we have all the output, no problem. It worked all fine, optimal. BAU is optimal. And let me double check. REN is optimal. And we have the result. Bye-bye, Paolo. He's going to come back. Right? Yeah. I can see the future. And we are going to calculate the CO2 emission. Again, CO2 emission is not default value that you can get from the output from how do I say predefined as predefined output. So you need to put CO2 intensity into the model, and then you need to recalculate it later. So CO2 is going to be calculated something like this. Is what we need is CO2 output, which is basically the input generators CO2 intensity. This was the input that we had in the file, in the CSV file, in generators.csv. And for those without any value, we are going to change NA value, so not available value, to 0. And then, is it too small? I think it must be too small. Is it better now? Thank you, Nji. And we are going to calculate the emissions by hour. Emissions hourly is network BAU generators. Always, I told you, temperature is in T. Generators underscore T has the temperature. And what temperature do we need? We need the power output. And then we will multiply the power output to CO2 to the axis 1, which is by column. Right? And then BAU, total emission, this is not typo, total emission is emissions hourly sum, which is I'm going to sum to a row and then column so that I will have just one number, and we'll divide it by 100,000, which means Is it million? Yeah. Yeah, I think it's million, right? Because South Korea has a slightly different number, like way of number. So we divide, we calculate. How do I say? Like in case of U.S. system or in case of standard system, it goes by 3 digit, right? Like thousand and million and billion and trillion or something like that. But in South Korea, we go by 4 digit. Yep, that's something very confusing to me always. The reason that we divide this number by million is because we want to change kilogram to megaton, right? So we're going to run it and CO2. Let's double check if this number is correct. Then we have CO2 intensity of each generator. We are going to do the same. But before that, I'm going to share this code with you on the message just in case to make things be faster for you. And then for the second one, we are going to have just renewables as well, renewables output rather than BAU. So we change all BAU to REN. Then what we have now is we have BAU total E, which is total emission of BAU. If we run it, we have total emission of 307 megatons. This is the total emission of the electricity of Japan. And we have total emission of a renewable energy, high renewable energy scenario, which is 186, right? Much lower, about 40% lower or something like that. So, but we also want to know its intensity as well. I know I'm going pretty fast at the moment. After I calculate the intensity, I'm going to stop there and we'll give you some time to do this on your own computer, okay? BAU. So to calculate the emission intensity, we need to divide total emission with the total load, electricity load, right? Something like this. However, we need to be careful. If we just do it, then number is going to be way too small because this is megaton. So I want to turn it to kilogram. So that this unit is going to be kilogram per megawatt hour. So now we have 0.294 kilogram per megawatt hour. We can do the same for renewable, right? So as we can see, renewable energy, high renewable energy scenario has much lower emission intensity. So I'm going to bring these numbers back to the table. So in case of BAU, it has 307 megaton, right? Then I'm going to ignore all those numbers after decimal point. And then in case of renewable energy, it has 186 megaton of emission. What about the intensity? So in case of BAU, its intensity is 0.294, 0.294. Sorry, what's a mistake? No, ton is correct. Yeah, so ton per megawatt hour. I think I made some mistake with my unit as this became. Anyway, I'm going to put these numbers back and then I will double check it. And its number, let me see here. So this is how we calculate the CO2 emissions and CO2 intensity. However, here I made a mistake. This cannot be megaton. I think this needs to be ton. I think it needs to be kilogram to Kton. But then if this is Kton, this entire number doesn't make sense. 107 Kton in Japan is too low. So I will just assume the original number was ton. This is ton per megawatt hour. Ton per megawatt hour. I will change the unit. Yeah, this is correct. I think it was just a mistake of this comment, right? So I'm going to stop here and then I will give you 4 minutes to replicate. We already have a number for the Philippines is 90 megaton. So that we already can see Japan emit about 3.2 times more than the Philippines. However, in terms of the intensity, the Filipinos electricity grid has much higher carbon intensity than Japan, which means although total emission is lower, it has more coal share and more gas share, higher gas share than Japan. It's fine. You can feel it later after the course or during the mid break. We can jump into the next part. Because I want to finish this part and then we'll take some break and we will wrap up the entire semester. Okay. So the last one we are going to calculate is basically the cost, right? Whenever we talk about if this new power scenario is reasonable or not, there are a couple of things that you need to check. One is the reliability, and another is generation share. For example, if you have 100% renewable, like 100% just the solar or 100% wind, it is very highly unlikely to be realized because of the variation. You need some huge amount of ESS or backup stage in that case. And the last one, probably the third one that you need to check is the emission, because that's one of the big topic that we are always talking, right? And the last one that we discuss usually is the cost. If this high renewable energy scenario is cheaper or not. Okay. Yeah, it's fine. So what what we needed to calculate now is going to be the LMP. So it will be look like something like it will be look like similar to this one, but we are going to work on our own notebook. So first, we need to calculate. We need to understand. It's not really calculating because pipes already calculate all the cost and everything. All we need to do is get the numbers out of the framework. So where does the number exist? It is in the network, and the cost is on its own bus, right? On node, and then need to go for marginal price. If we just enter it, we can see the marginal price of the bus because this is just one node system, so we don't need to make multiple node, but it's just one node system. So we can get the value of the bus. Let's see only the first 440. So maybe just 10 days. And then let's plot it easy. And this is the output of a BAU scenario. I'm going to copy this output to the week 8 at this one. But we'll jump into Japan. And then we'll format the option size. It's just 5. Okay. Now we have one output. And then let's do the same for renewable energy scenario as well. All we need to do is just change BAU to BAU network to renewable energy network, because those two networks has different name but has exactly the same structure. So that if we copy and paste the output, we can now compare those two. Okay. Let me change it to be the same size. And then let's zoom in. So we can see slightly different output here. So for the BAU scenario, basically the baseline, or how do I say, the median price is going to be about 8.5. If I remember correctly, 8.5, whatever the currency per megawatt hour. However, there were already 1, 2, 3, 4, 5, 6, 7 peaks, but in case of renewable energy scenario, it has the pretty much the same median price, but it has only 4 peaks. And then when we see the width, BAU scenario has been more bit thicker width, which means the higher or peak price remained the longer hours than renewable energy scenario. Not necessarily better, however, definitely it's cheaper, right? So in terms of the lowest cost, BAU scenario goes down to probably about $3 per megawatt hour, three currency per megawatt hour. However, in case of BAU scenario, it goes down to zero. How does this be? Why does this electricity price can go down to zero? Because sometimes for some hours, in this case, it's not really some, but almost every noon or almost for every afternoon, solar and wind generate 100% of its electricity. And solar and wind in this system doesn't have marginal cost, so it becomes zero marginal cost electricity, so that electricity becomes just a free, right? So using more electricity is actually economically beneficial for you. For yeah, in many cases, if we have a higher renewable, then it can be economically beneficial. And what we want to see also is, let me just copy and paste this part. But what I want to see is the sum. So in terms of total payment of the entire year, the BAU scenario paid 92,563, whatever the currency. But in case of REN scenario, it paid 57,000 or 58,000. So about 40% lower than BAU scenario, which means basically having more renewable energy is going to be economically beneficial for this system. So really important to remember is this output cannot be applied to everywhere, right? This output, we can get this output only because we assumed that renewable energy doesn't have any marginal cost, right? That is the reason. So when you model it, when you explain your result, you need to explain what was your assumption and what was your input data. And then you can say, based on this input data, this is the output we have. So it's much safer than just showing, oh, this is the truth, right? Because model never show you the truth. Model only show you what you want to see. Okay. Thank you so much for the first half of the last session, and let's take 10-minute break, and we will come back and we will wrap up the entire course. Okay. Thank you. See you soon. So shall we begin the last session, last half of the last session? So thank you so much for filling in some numbers here for South Korea. So yeah, this is very reasonable number for South Korea. Basically, South Korea's electricity intensity is slightly higher than, I mean, about 30% higher than Japan. However, their emission is much lower because Japan uses much more electricity than South Korea. So in case of a high renewable energy scenario, because Japan has a higher renewable share at the moment, it is quite understandable that still intensity of South Korea of a high renewable energy scenario is higher than Japan. This is good. I think it's a good result. I mean, saying good or bad is not really relevant here, and it sounds too much Trump, but still, it's a quite reasonable result to analyze. Very good. Thank you so much for following all of this. And then, if you have time, it will be great if you can fill the other part as well. The cost part as well. So just to graph, and then also if you can add some like LMP annual cost of the system, that will be great. So now let's wrap up the uh, entire cost. Oh, there is a Philippines and South Korea coming in. Let me wait, and then let's see the result and let's analyze it together. So we have Philippines first. Interesting. So in case of this BAU system, probably is on the top. The highest price is going to be about $22.5, maybe five currency, and it always goes up to the top. I think it will be some in afternoon or just before the afternoon. I don't know yet, but then when the Philippines has a more renewables, then there are some days where renewable provide much more, so that more expensive, I don't know if this is gas or something, but more expensive generator will not jump in to the grid, so that there are 3 days where the electricity price becomes only the half of, bit higher than half, about $15. So 15, so 15 about 30% lower than BAU scenario. So that having higher renewable energy scenario in this case also can reduce the entire electricity price. Same for the annual price. When we see the annual price, BAU has about 98 thousand something currency, but in case of renewable, it becomes 89 something currency. So it's quite interesting. It doesn't reduce much, but still it reduces renewable energy can reduce about 10% of its marginal price in this scenario. Let's go back to South Korea. In case of South Korea, it looks quite similar, somewhat similar with Japan, but when we compare the BAU between South Korea and Japan, one big difference is in case of South Korea, the price doesn't go below 8.5 currency. But if we see Japan, sometimes it goes down to 2.5, which implies that there are some times or snapshot when probably more expensive generators doesn't jump in Japan. However, in case of South Korea, probably there's just one. Probably there are only two power generators, be less expensive and be more expensive, probably coal and gas, which will decide the S&P of every time minute. I mean timestamp. But in case of high renewable energy scenario, interesting thing that we can find is we can see the electricity price goes down to zero. Same with Japan. So which means South Korea can rely on 100% renewables at some time point, probably in the afternoon when there is enough solar, because solar is the major electricity provider um, in solar is becoming major electricity provider for the high renewable energy scenario in South Korea. And when we see the annual price, basically high renewable energy scenario has about 30%, I think about 30, maybe less than 30, about 25 to 30% lower annual electricity cost compared to the BAU scenario. Thank you so much for sharing this output. This is very interesting ones. And then I will run the other two countries, Pakistan and Indonesia, probably about 30 days later if no one fill in, but I'm pretty sure somebody from Indonesia and Pakistan will fill the other numbers as well, like you guys did before last week. And then I will make this as a very short, not really report, but very short slide to share with everyone on our Notion website. Thank you so much for this. This is not the best way to share. I don't know, but probably let's go for this one first. Let me see if this works. So this is something that I made, and then this is open source, so you can find it on my GitHub. And then, yeah, let me share my GitHub screen, GitHub link. So for those who want to see, actually, Planet has GitHub, and then we basically share basically all our output as a publicly available open source. So these are all open source tools that you can use. And then here is the GitHub link. I'm going to share it to the message so that you can click it and then see it if you want, and you can see our effort. So this is very simple approach of pipes, very simple tool using pipes. So we have a system setting. So annual load is say 700 terawatt hour. I already put the load profile in the data file as well, in the data file. So that what annual load is doing is it basically adjusts the profile based on the total amount. So for example, if the total amount of this load is 500 terawatt hour, then if I want to achieve 700, then multiply all values 700 and divide by 500 so that you can scale it up. And then we can decide what kind of solver we are going to use. Groovy, Cplex, I added them, but they are paid and it's very expensive, so I don't use them. But Highs is the base one that I almost always use. Yes, this is basically based on Streamlit. Yes, Charles. So I use the GUI Streamlit. That's pretty much the simplest one. And then what we can change is a solar generation. We can fix the capacity, or we can change the solar generators are extendable. And then you can set the minimum capacity and the maximum capacity here as well. Yeah, something like this. And then you can change the capital cost and marginal cost. Same for the wind. You can set the minimum and the maximum. And then next one, you can have a nuclear power. And then lastly, you can have hydrogen. Of course, hydrogen and nuclear can be also extendable as well. Then lastly, we have the battery, and we can run it. Let's see if we can find optimal solution here. I'm sharing this just to tell you that you can make something very simple and but still interesting ones using PipeSA. It takes a little longer time than normal. Yes, now we have the output. So this is the output, total cost, and then total generation. And then also we have a storage power, and time snapshot is 2024. So we have 24 hours more. And installed capacity of solar is 378 gigawatt and wind is 137 gigawatt. And their capacity factor is 9% and 18% each, because we lose a lot during when because we need to curtail the wind and solar output, right? And then we have ESS. However, it's not used very actively. It's only 4.3%. But if we don't have ESS, then we are going to need, I don't know, 1,000 and 2,000 wind power or something like that, because of those times when we don't have sunshine and when we don't have really much wind. So this is basically the share of generation share, and then we have energy system operation result. So we can just zoom in to something like this. So we have the green one is ESS charging, one going down is ESS charging, and then here is a red one with ESS discharging. So basically ESS, this part is charging the ESS from solar and then use this electricity later, which is called load shifting. And here is the result of how the ESS being used for those selected 4 days. And then ESS state of charge. And we can download the entire output onto an Excel, which is simple, but quite useful tool when you analyze one node model in a simple way. And there is another one that I created, which could be a little more interesting. So this is technically I didn't use any pipes here, but this is pipes are related tool, because what this tool is doing is you can add a bus here and you can add a bus here as well. And let's assume there is a electricity load, and then this load is connected to which bus? It's this one, E9CF. Is load is connected to this here. So we can see those two are connected, right? Those two are connected. That is the electricity load of New York. And then let's assume there is a somewhere, I don't know, I have no idea, but let's assume there is a hydro generator which is connected to the generation bus. And probably here is some, I don't know, wind or something like that connected to generator. And also we need a line which will connect those two buses like this, right? And then we have a storage which is connected to, sorry, don't need it. Doesn't matter. Let's leave it here. And we can simply delete it. And then we can connect it to the New York. So it becomes something like now behind the meter, but to be behind the meter, to be honest, is just too big because it's connected to the load of New York. And then what we can do is export it to Excel. Let me show you the output is coming in. Actually, where is my Excel? Give me 1 second, it's coming in, but takes a little time to load. Yes. Now we have the output here. So we have the output of the bus, we have the output of the generator, we have the output of the load, we have the information of the line, and we have information of the storage as well. And if we want to add some more information, for example, let's say this generator has something named wind, you can change it. and then you can change the carrier to be wind, and then you can change its nominal power to 100 megawatt or something like that. Then you can save it. For this case, it's 200 megawatt or something like that. Then this tool will be able to will help you to build the model in easier way, right? I So this is something that I'm working on at the moment. So it's not perfect, but something that I would like to share with you too. Then I'm pretty sure this will make your life easier when you do the modeling on PyPsa. Yeah, and the last thing I want to tell you is if you go to the message, there is a link to the form. It's basically the evaluation form. Let's share the link with you. It's this one. This is a link to the yeah. I shared the link in the message, and if you can fill this evaluation form, that will be really great for us. And it's, as you can see, email is not shared, so it's totally anonymous. So don't worry about it. And please, if you provide us your honest opinion about this course, that will be really great, and it will be really appreciated because we can make a better course for the next semester and the next year. Okay. And yeah, it's a little too early than I expected, but thank you so much for taking my course. And yeah, thank you so much. And hope you guys enjoyed this course. And if you have any questions, or if you have a plan to make your own like power model of your country, and if you're having trouble, please contact us. We can definitely help you to build a good model with you guys. Thank you so much. Please fill the form. Please leave us the feedback. Thank you. See you later.